Okay, I want to look at um, what is called Atwood's machine. I'm sorry, I'm getting a text from my wife. So Atwood's machine, I guess it's just a guy who studied pulleys. They have modified Atwood machines and just Atwood machines. I don't know why. I guess they wanted to give the guy some credit, so they named this after him. It's just a pulley that uh, is either mounted or hangs from the ceiling, uh, so it can rotate about its center. So I'm just going to have it hanging from the ceiling. The pulleys, in a sense, the pulley's fixed. It can't move up and down, right or left. And then we hang a couple masses on it. So we'll have M1 and M2. And let's make M2 greater than M1. So we'll start with this situation, and let's start with the situation where the mass of the pulley is um, very small. Very small. So we're going to ignore the mass of the pulley to start with. All right, so I want to know the acceleration of the system, because you know if M2 is greater than M1 and you're sitting here holding it, you let it go, it's going to start to fall. This one's going to go this way and that one's going to go that way. There is a constraint on the system. These two masses are connected by this piece of string. So they're constrained to move together. So if we call up positive here, then we have to call down positive here because they're moving together. Okay, so for this block, up is positive. For this block, down is positive. We have to be consistent. We can't call, because they're moving together, we can't call this positive and this positive. It doesn't work. So I want to know the acceleration of these blocks. Okay, so let's look at each block individually first. So we do a free body diagram of M1 and M2. So here's M1, and here I'll have M2. Now nothing's happening right to left, so there are no forces right to left. It's just it's being pulled up, gravity's pulling down. So on M1, we have the weight of 1, which is M1G. And on block 2, we have the weight, I'll draw a little bit longer, we have the weight 2, which is M2G. We have the tension in the string, so I'll call that just T. And we have the tension string here. Because the pulley is massless, these two tensions can be assumed to be the same, so I've tried to draw them the same length. They are not balanced here because M2 is greater than M1, so this tension is going to be greater than W1 and it's going to be less than W2. So I have a problem. I don't know the tension and I don't know the acceleration. So there's basically two unknowns there. So I'm going to need two equations. So let's develop the Newton's second law equation for both blocks, because that'll give us two equations. So for M1, the equation would look like this. We have T in the positive direction minus M1G in the negative direction. The weight of block 1 is going to equal M1A, because this is all about block 1. So it'll be MA would be the mass of block 1 times A. Okay. For M2, we're going to have, now down is positive, so we're going to have a negative T plus M2G equals M2A. So notice now we have two equations, two unknowns. when I see something like this and I see a negative and a positive, the easiest way to get rid of that tension is just add the two equations. When you add them, t and a minus t becomes 0. We have m2g plus a minus m1g, and on this side we have m2a plus m1a. Okay, we're looking for a, so I'm going to do a little factoring here. I'm going to factor m2 minus m1 times g equals m2 plus m1 times a, and then I'm going to divide by that. So we get a equals m2 minus m1 over m2 plus m1 times g. Okay, let's see if that makes sense. You can put parentheses around them if you want to, if it looks better to you. Let's go to extremes. Let's say m2 and m1 are actually equal, and you let go of them. What would you think would happen? They'd just sit there. They're balanced. Same mass on both sides. So look in this equation. If m2 and m1 equal each other, this is 0, so there's no acceleration. So that makes sense. What about if m2 is the size of a freight train and m1 is the size of a BB? You would expect m2 to just fall like m1 wasn't even there. So it would fall with an acceleration of g. Let's see if that's what happens. If m1 is negligible compared to m2, then you basically have m2 minus 0 over m2 plus 0, which is m2 over m2. The m2's cancel, and you just get g. So this makes total sense. Okay, now let's complicate things just a little. Let's see how it changes things. Let's say now that the mass is not very, very small. It has a mass MP and a radius R. Now we can no longer assume that these two tensions are the same because this pulley is going to provide some resistance to motion. So now we're going to have T1 and T2 here. Does this situation change anything about the forces on M1 and M2? No. I mean, you isolate them, look at them. When I say isolate, I mean draw a little like line around them and say, okay, what's messing with M1? Just the string and gravity. The pulley's not touching M1. M2's not touching M1. It's the string that's touching it. So these two equations will still be valid. What changes? Well, now we have something going on with this pulley. It has torques applied to it. It has a torque here of T1 down and T2 down, but on opposite sides. So this, for the pulley's point of view, if we look at the pulley, we no longer draw it as a dot. We actually draw the pulley and draw the forces acting on it. And you have T1, T2, and you also have gravity acting on the pulley, but it can't move up and down. I mean, you could draw gravity acting down on the center of the pulley and this other string, call it T3, pulling up on it. And I could ask you what would be the tension in that string. Well, it would be the weight of all of this. Okay, so, but I'm not asking that. I just want to know, okay, what's the acceleration of the system now? Okay, so if we have one more, well, now we have three unknowns. We have T1, T2, and A. So we need a third equation. These equations will become T1 minus M1G equals M1A, and a minus T2 minus M2G equals M2A. Okay, so we need a third equation. So what we're going to use now is Newton's second law for torques, for rotational motion. So if we call up positive here and down positive here, then I'm going to think of positive torques being this way, because they would cause it to rotate that way, and negative torques this way. So we're going to have the torque from T1. The torque from T1 is going to be negative, and it's going to be how far it operates from the center, so that's R. And it's going to be the force, T1, and then the sine of the angle between them, but that's 90 degrees. Moment arm's right here, this is 90. So it's just 1. And then we have plus R T2, okay, trying to rotate it this way, and that's it. That's the total torque acting on this thing. Well, that has to equal I alpha. So this is Newton's second law for torques. It looks like this. The sum of the torques equals I alpha. It corresponds to the sum of the forces equals MA. Notice force, torque, inertia, rotational inertia, acceleration, rotational acceleration. Okay. All right, so now we have to figure out how can we get rid of these T's now to get A. How is A connected to alpha? Well, we know if there's no slipping or anything going on that A is alpha R. We also know for a pulley, which is the same thing as a disc, which is the same thing as a cylinder, it's 1/2 mR squared. So let's do some substituting, and we get a minus RT1 plus RT2 equals 1/2 the mass of the pulley times the radius squared times, I'm going to substitute in for alpha, A over R. Okay, because we have alpha here, so alpha would be A divided by R. So notice something weird here. The radiuses cancel, because this R squared cancels that R, and there's an R in every term. So we have a minus T1 plus T2 equals 1/2 MPA. All right. So I don't know how you go about doing the algebra from here. We want to get rid of T1 and T2. So if we add all 3 equations this time, would that work? I mean, think about it. This T1, negative T1, so that would cancel. Negative T2, positive T2, that would cancel. So yeah, let's just add all 3 equations straight down. So on the left side, the T's would all cancel. I had a sign wrong here, y'all. I'm sorry. I transferred that down wrong. So we have M2G minus M1G on this side. That's all that's left. And on this side, we have M1A plus M2A plus 1/2 MPA. So we have, factoring again, we have M2 minus M1G. And on this side, let's factor out the A. We have M1 plus M2 plus 1/2 the mass of the pulley times A. Divide by what's the parentheses there. We get M2 minus M1 over M1 plus M2 plus 1/2 the mass of the pulley, all times G. So what it did was it just added an inertial term that would make the acceleration less, because we've increased the bottom, we've increased the denominator here. If you increase the denominator, it makes the fraction smaller. So the acceleration of this system would now be less by that factor. Everything else still holds true if you think about it. I mean, if m2 equals m1, it's still not going to accelerate, so this is 0. If the mass of the pulley is gigantic and m1 is small, it's not going to accelerate at g anymore, because the pulley's going to keep it. It'd be like having a, let's say, a railroad wheel hanging here, and a BB and a bowling ball for T2. It's going to accelerate, but not near like G. Still be a lot less. All right. So I hope this helps with understanding a little bit about utilizing Newton's second law for both rotational and just linear motion.